Hello, judges. My name is Antonia Kolb, and my project this year is Detect It, a machine learning-based application for real-time tick identification and spatiotemporal disease risk assessment. Every year, the Centers for Disease Control and Prevention report that 50,000 people are diagnosed with tick-borne diseases in the United States, and this includes Lyme disease. However, underreporting discovered suggests the real incidence rate is much higher, closer to 500,000 cases per year, some of which are fatal. Now, 2 years ago, I was actually diagnosed with two rare systematic tick-borne infections, which prompted the creation of my app. And due to underdiagnosis and asymptomatic clinical manifestations, the scope of this public health threat is difficult to assess, leading to delayed diagnoses and treatment. And the issue is that the prevalence rates of different disease-causing pathogens vary based on geographic locations and species of ticks. And correct identification of ticks is difficult for the general public and even for some healthcare professionals due to minute feature-wise differences. So given that human experts are the limiting factor for diagnostic capacity in this field, as well as the pressing health concerns over tick-borne diseases worldwide, deep learning-based models such as computer vision-based approaches with transfer learning used in prior literature mentioned here hold promise with 93% reported accuracy for the instantaneous assessment of tick-borne disease risks. So this project's goal was to create a machine learning-based mobile application that could identify the 10 most disease-causing tick species in real time and provide a location-based tick risk assessment by embedding the Center for Disease Control's spatiotemporal tick and pathogen surveillance statistics. And for user accessibility, an iOS mobile application with other useful features was deployed onto the Apple App Store in 2023. So for the first iteration of this project, a neural network that could accurately identify the three most disease-producing tick species was created. This was used to identify the American dog tick, the eastern black-legged tick, and the Lone Star tick. And Inception v3, a convolutional neural network, was used for this version of the app, reaching an accuracy of 80%. But actually, after closer examination, the model was overfitting, or misclassifying ticks and non-ticks. So a new architecture was chosen to ultimately identify all 10 of these tick species using ResNet 50v2, which is a deep convolutional neural network that uses transfer learning and will be explained shortly. So for the learning models, I collected images of ticks and cleaned the noise from readily available data sets on Google Images and other image platforms to ensure the data set used was morphologically correct. And to prevent data leakage between classes, a two-step data split process was performed in addition to data preprocessing and data augmentation to increase the data variability. And this is vital in machine learning projects to safeguard against data contamination and bias model evaluation. But again, ticks are very small, ranging from 3 to 5 millimeters, with varying appearances that are difficult to detect by the human eye, as well as for some convolutional neural networks. So to overcome this project, I placed tiny black squares on the images to generate noise and enable the model to pay closer attention to minor feature changes such as color, distinctive dots, and shape. And after applying the black dot method, the model showed an ability to generalize or to distinguish between species, which was later used for the 10 ticks. Now, the architecture of the model is crucial for the performance, so different convolutional neural networks were tested and compared. Now, the first objective was to create a convolutional neural network capable of identifying the three most pathogenic tick species as seen before. So the first transfer learning models tested were ResNet 50v2, a 50-layer deep architecture, ResNet 152v2, an improvement of ResNet 50v2 with more layers, and Exception, which is used for feature-wise detection. And so unlike the other models tested here, Exception performed well and was not overfitting, as seen in its consistency of training, validation, and testing accuracy metrics. So it was chosen to identify 3 ticks. Now the dotted line denoting the testing accuracy was around the training and validation accuracy, while the other models' training and validation accuracies were well above the dotted line. Now, while Exception model worked well for the 3 species, the architecture had to be reevaluated for the implementation of 10 species classification. The same networks, ResNet 152v2, Exception, and ResNet 50v2, were tested and evaluated with the addition of MobileNet v2, which is a lightweight architecture often used in mobile applications, which is efficient but not as complex, so it was not actually used. And both ResNet 152v2 and Exception are computationally intensive and had similar results to ResNet 50v2, as you can see in the graphs. So ResNet 50v2, an improved version of ResNet 50, was chosen for the task of identifying the 10 species because it balances efficiency, performance, and would allow for future facile fine-tuning and hyperparameter tuning, as seen here. So my model showed promise, but once again, the size of ticks was extremely challenging. When real-world photos of ticks that featured occlusion or tiny ticks were trained, the model accuracy dropped, and most of the issues were related to the model not detecting a tick present. So I implemented a novel method, namely the window algorithm, which continuously crops the photo until over 95% confidence is reached by the model, as seen here, with regard to the tick species classification or whether a tick is present. But as more species were added, the neural network misclassified certain types whose interspecies differences are highly refined, but their geographic ranges are different. For example, it's rare to find an eastern black-legged tick in California or a western black-legged tick in Connecticut. So when the user takes a photo of a tick with the app, their geographic coordinates will be assigned to a respective state or country if outside the US, and the species will be confirmed using the CDC's state surveillance data. And the information from the spatiotemporal risk assessment feature of the app was used from the CDC's tick-borne pathogen surveillance data for the 12 identifiable diseases. And due to the lack of information available in certain areas, location-based weighting was applied to the data set based on population size and proportion of infected individuals from tick bites to predict the risk of infection if a user in a given region is bitten. So here's a schematic of the detected app with a tick bite pipeline. Users can take a picture of the tick they find. The backend will identify it among other advantageous features. And for easier public use, a gradient scale from low to high level of danger was implemented while still providing access to a full risk breakdown. And prior to taking a photo of the tick, the user can fill out a form that provides ground information for their risk assessment, such as engorgement status of the tick and whether an animal or person was bit. So Detect-It was originally developed in Xcode with Swift within a service-oriented architecture. So after the convolutional neural network was ported from a local environment to Amazon Web Services or AWS, open application programming interfaces, also known as APIs, were created for functions such as specimen identification, location finder, and risk assessment. And using this approach, Detect-It is able to scale through AWS's Lambdas functions, thereby delivering results to the app's users in mere seconds. So to evaluate the performance of the neural network's ability to identify the ticks correctly, confusion matrices and other performance metrics can actually be analyzed. So the model was first evaluated for 3 species, 6, and later for 10. So here we have the test and validation confusion matrices for the 3 ticks prior to implementing the window algorithm. Now, the ideal result is to have a diagonal line across with little errors outside of the diagonal, such as that. And this is after applying the window algorithm. As you can see, the window algorithm greatly improved the accuracy of the model, as seen in the decrease in errors. And this is the test and validation confusion matrix for the 6 species. The first matrix is with the window algorithm prior to implementing the location-based heuristic algorithm. And this is after applying both the window algorithm and the location algorithm. Once again, the errors greatly decreased. And the next one is for the 10 species after implementing the window algorithm. As you can see, minimal errors occurred in the distribution. And the last confusion matrix is after implementing the window algorithm and the location-based heuristic algorithm for the 10 species. This has even fewer errors when both algorithms are applied, since interspecies similarities were eliminated due to locational differences.
Antonia, you have just over 2 minutes left.
Perfect. And this table indicates the results from the confusion matrices with a 97% overall accuracy for 10 species. So while a machine learning-based approach for tick identification has been explored, this novel mobile app can identify the 10 most common and disease-causing species and predict the risk posed by each tick. And based on literature, this is actually one of the first implementations of a machine learning-based app that can identify 10 species with high 97% accuracy, as well as provide a qualified assessment of the potential risk of infection. And the implementation of the window and location-based heuristic algorithms are both promising for tick-based identification and potential with medical imaging, where minute features are difficult to detect. And there are current limitations with the availability of data in regard to tick photos and tick-borne disease surveillance databases. And due to the lack of available data, transfer learning was actually utilized in this capacity to compensate for any data disparities. But future versions of this app include expanding the geographic regions to other countries, data availability permitting, and to provide this service more globally to tick bite victims. And the knowledge and confidence gained will facilitate diagnostic accuracy and shorten critical time to treatment, likely providing a better quality of life for affected individuals. Now, Detected is currently available on Apple's App Store and is free with 2,000 downloads. Thank you. I'd like to thank my teacher, Dr. Schulman, and my mentor, Maximiliana Armesto.